we're going to talk about springs now. So a spring, coil, wire, it could be lying horizontally, vertically. We briefly mentioned, but we didn't do anything with it, the force that a spring exerts on an object. This equation is called Hooke's law. It is the force by a regular spring. The negative sign means that the force is opposite whatever's done to the spring. So delta S represents the stretch or compression. So the spring that I've drawn, if I were to hang a mass from it, this spring would stretch downwards. But the mass would feel a force upwards from the spring. That's what we mean by the negative sign. The force the spring applies opposes or is opposite to that displacement. So delta S represents the displacement of the spring. We can specifically say how much it is compressed or stretched from equilibrium. I'll explain what I mean by that in just a second. K is called the spring constant. That is something unique to this spring. It basically explains how strong the spring is. A larger spring constant means a stronger spring. So as long as the spring still behaving like a spring would, then that constant is valid for the spring. It does have units. It has to have units of newtons per meter, because we're going to multiply by a displacement to get the force. Newtons times meter times the displacement in meters is going to give us the newtons, thus the force of the spring. All right, so our spring. So let's say we had that original spring and I've hung a mass from it. And this mass is hanging at rest. We could calculate the spring constant if we were able to calculate the distance the spring stretched from not having the mass on it, and if we knew this mass. If this mass is hanging at rest, the force of this spring upwards would have to balance the force of gravity downwards. If those are equal in magnitude, we can say K delta S is equal to mg. Let me write that better. So if we knew the mass, we know G, and we could measure the delta S, how far that spring stretched when we hung that specific mass from it, we could determine the spring constant of a spring. Now, I know if from this resting position, if I were to grab this mass and pull downwards and then let go, so if I pull down farther and let go, I'm trying to figure out where to draw. So same spring, but I've pulled down and I let go, I know the spring is going to pull that mass upwards. It's going to make it move. The spring is going to do work on the mass. And so it will make the mass speed up. But as it continues upwards, it's going to slow down because of the force of gravity and eventually reach a maximum height. And then it's going to fall back down. And it's going to do this up and down for a while, depending upon how much thermal energy is created while the spring and mass are in motion. So we're going to look at the work done by a spring. And we can account for a spring by this work, which is part of the reason we wait until now to cover and solve problems using springs. So work done by a spring. The force itself is varying. And so if the force is varying, we do need to integrate force dotted with displacement. So the force is always opposite the displacement. Okay, I personally don't like writing delta S and having a ds in my equation as well. So I'm going to go ahead and write the force of the spring as negative Ks, but we have to keep in mind we mean delta S. So a stretch or compression from equilibrium specifically. All right, so since our variable in here is ds, s is our variable, and our limit will be between some initial position to some final. And by that, I mean specifically initial stretch or compression to some final stretch or compression. So how much the spring is stretched or compressed initially, and how much it's stretched or compressed finally. When I integrate, the k is a constant. I'm going to get s squared over 2 because that is our variable. So plugging in my limits, I'm going to have an s final squared minus a negative 1/2 k s initial squared. You'll see this equation in the test notes with the delta s's, which is totally valid. For me, it's just a personal preference of not liking to have a delta and a ds together, too many variables and representations in my mind. Excuse me. So these equations are the same thing. We can calculate how much work a spring does if we know the spring constant, that's what K is, and if we know how far the spring is stretched or compressed finally, so final delta S, so stretched or compressed, and then initial delta S. If at one moment in time the spring is not stretched or compressed, then the delta S would be 0. So ultimately we need to remember that S is measured from equilibrium. So for example, let's say, just for simplicity's sake, we have a spring and a mass and this is the equilibrium position. I'm going to represent that as 0. So the equilibrium position means there would be no motion. This spring with the mass would just be sitting there. So the system of the mass and the spring together would be at rest. If I take the same system, and that floor is supposed to stay horizontal, and I pull the mass to the side, this would be my S initial or delta S initial, whichever way you want to look at it. I will have stretched the spring, and therefore I now have an initial stretch. So whether I'm using the equation without delta or with delta, same thing. We're now saying that there is this initial term in either case. If I let go of the mass, I know it's going to start moving. If I let go of the mass, it will start moving to the left. It will speed up as it continues to the left because the spring is pulling on it to the left. Remember, the force of the spring is always opposite the displacement. So the force of the spring being to the left means there's an acceleration to the left. It's going to speed up. But as soon as the mass passes through equilibrium, even just barely, it's still moving to the left, but the force of the spring will then be to the right because the compression S or delta S is now negative, so the force becomes positive, which means the spring is going to slow the mass down until the mass stops. And then the spring will push it in the opposite, keep pushing on the right, and the mass will speed up to the right. So the work done by the spring overall on any given system depends upon some sort of initial and final moment in time. We've been talking about that already, where we say the net force is equal to the final kinetic energy minus initial kinetic energy. I don't know that I've explicitly stated initial versus final. Initial was a starting point in time and final an ending point. One of them was the moment we knew the answer for. The others typically where we're trying to find. This is similar. The work done by the spring depends upon two moments in time that we're talking about. And we will choose one of those moments to be something we know the compression or stretch of the spring, and the other will be somewhere we're trying to find answers for it. So springs, we'll go ahead and do a couple examples so that you can see how to account for springs in a problem. Now, as we move into chapter 10, we're going to be talking about potential energy. I personally like using conservation of energy over work. Net work equals change in kinetic energy. So I will get there quickly, ultimately. We're going to jump to conservation of energy pretty quickly, which is just building on what we're doing right now.